Alrighty, I guess we can start now. Good morning, good afternoon, good evening, everyone, wherever you are, and welcome to the plenary 10A session, which will be based on using FRB as cosmological probes. So in the previous few days, we have learned about FRB properties, their progenitors, and we had a really good discussions about all those topics. And today we are going to focus on using them as cosmological probes. We have some excellent talks lined up for these sessions, and it's a mix of live and recording talks. So we'll be starting up with Yuli Pen from CITA at the University of Toronto, and he's going to talk about FRBs, coherent probes of space-time. And it's a live talk, and yeah, all yours, Yuli.
Thank you. Let's see if it works again when we actually need it. Here we go. So are you seeing the full screen PDF?
Yes.
Well, welcome everyone. My pleasure to give the first talk, which is still daylight here for the next couple of minutes. You can sit on my patio. And I wanted to give some of the aspects that I find very exciting for FRBs that actually I feel also a underexplored application that I encourage people to think more about and to use more on data. So let me start. The basic properties that I want to use is their coherence. Coherence means that they form an interference pattern under multipath propagation, and I'll talk more about what that means or how that works. This enables a new handle on some old concepts, for example, gravitational lensing. And I'm going to talk a little bit about how this impacts attempts to do gravitational microlensing and gravitational macrolensing. And the more mature lensing application is plasma lensing, which has already been observed. I mentioned that just very briefly. So that opens up the window to use FRBs to probe the universe, what the universe is made out of, perhaps the nature of general relativity or whatever other theory might replace that. And yet another application of this coherence is that we can use these lenses, be they gravitational or plasma lenses, to learn about FRBs. So it's a two-way street. And you might wonder if that's not a circular problem, but we'll get to that. Let me just start off with just the concept of coherence, which is a very uncommon phenomenon in daily life on Earth or on the sky. So very few objects exhibit what I would call diffractive, what people call diffractive scintillation. By diffractive scintillation, what we mean is that the light takes multiple paths towards us and that these paths form an interference pattern. One thing we do see is, for example, twinkling of stars. The atmospheric scintillation can make stars appear to twinkle. And the twinkling is a bit chromatic. It's much more dramatic for pulsars and fast radio bursts that are known to strongly modulate on very narrow frequency intervals and on modestly short timescales of seconds to minutes. So this means that these are the two objects for which you actually can think of them as having a double or multi-slit experiment along the multiple propagating paths. And this has already been observed. And I know last week we had discussions about whether this would happen or not. And I just want to encourage people to look at data and to, just quantify how much it does happen, or if it doesn't, how much it does not. And I'm going to make the general advertising that the plasma lensing is a proof of existence of the compactness and coherence of fast radio burst sources that implies that gravitational microlensing or general gravitational lensing is likely observable. Why didn't it change page? Here we go. So I'm just going to summarize a few known results. One is a relatively old one, that's from 2015. That's in this field. This is eternity, one of the first papers in the field, it seems, that FRB110523 is a scattered FRB that was detected at GBT by Shoshen and analyzed by Qiao. That shows scintillation of the scattering tail, and why that's not, I'm going to explain why that's non-trivial in the next slide. More recently, FRB 2011-24A showed a measurement of a scintillation time scale, and that was just posted recently by Main et al. And this suddenly allows us to analyze FRBs the way that some of us have been analyzing pulsars and using pulsars to analyze the space-time between us and them. I'm going to mention some examples for the crab that is giving us direct evidence for very high Lorentz factor of the emission region, with a very narrow spread of Lorentz factors. So the coherence of the emission has been one of the open mysteries. And while I think it is fairly apparent that a high Lorentz factor makes a lot of the problems much easier, there have been two big challenges to it. One is, why would you have a high Lorentz factor? And then even if you did, how can you get a narrow banded observed features, which are common in FRBs, unless the spread of Lorentz factors is very small, which seems contrived, unless of course it's been measured. So that's why I think these measurements are a big hint and a big lever arm to try to understand mechanisms. So these high Lorentz factors allow you to use, I'm just going to float some words around. Maxime has a beautiful paper on the free electron laser mechanism. A while back, 1971, what's that, 50 years ago, Sterling Colgate already was talking about the gamma squared mirroring effect that may lead to coherent emission. So that's not a very new idea. And that these all may have implications for FRBs, and mostly these are very accessible studies. This may just be a matter of looking at data that already exists. Okay. Now I'm going to speculate a bit about other types of measurements that uses the nature of the coherence of the emissions. If source is really a point source, then under gravitational microlensing, you see two images. So there are two paths between you and the source. And these two paths form an interference pattern. So when you look at different frequencies, and I don't know whether Rafiei gave a talk on that, it allows you to instantaneously measure the mass of a lens, be it a star, planet, dark matter, or something else. There's also a very amusing effect based on imaginary images. So these images can be geometrically not insufficient to form a real image, but wave optics can again opens up the new phase space. And I'm just going to give you a dangle in this very short talk. It's going to dangle some, but I think are very amusing possibilities out there. And then, of course, if you have macro lensing, I'm going to spend another slide on that later on. That opens up the potential to measure something to nanosecond time delay, propagating over gigaparsecs. So this you have to ask, what could one measure with such precision? It's a very small, fine number, right? So just if you translate this into a strain, it's a very funny form of strain, but you have light moving along two paths for gigaparsecs, interfering at a nanosecond sensitivity. So there's something that you're measuring to a part in 10 to the minus 26. That's some of the best measurements, period. It's a very tricky one. So you might think, oh, can you measure gravitational waves that way? It turns out the transverseness makes it not couple with this funny geometric pattern. But if you had scalar gravitational waves, it would couple. So we had a paper on that some years ago to discuss it. And at the very bottom, I'm just trying to draw a cartoon, and which shows that if you have an emission, sorry, this is from a pulsar paper, but FRBs may or may not be pulsars. That doesn't actually matter for this purpose. If you have multiple paths going through a scattering screen, arriving at Earth and potentially observed at different observing stations, that allows you to measure a large number of things about the lens and about the source. Back to the gravitational macro lensing potential. So with Olaf, we discussed, analyzed the possibilities of what happens if you were to have a strongly lensed FRBs. A lot of ifs, and a lot of these things we'll have to wait until we actually see them. But there are some new ideas that one should think about. So traditionally, I mean, it's not a new idea to use gravitational lensing to measure a distance. You know, you measure, if you measure the size of an angle, the size in the sky, you measure a time delay. You might have all the ingredients you need to measure an absolute distance. And absolute distance is, of course, if your Hubble constants, dark energy, and other derived observables. But of course, over the years, I think to make this very precise, it's always been difficult to understand the lens models well enough, since there's both gravitational redshift, there's the measuring path differences, you need to know the asymmetries between these lenses. It's actually been tricky to make this into a very robust, precise measurement at the 1% level, which is what one wants these days to be interesting. Now, you can already see that, well, in normal gravitational lensing, you're lucky to measure a time delay to a few hours, and the actual time delay might be a few days. So you measure something to, well, let's say 1%. And you say, well, but if my systematics are also 1%, does it matter if I measure things more accurately? The answer is it does matter. If you now measure things to a nanosecond, the time delays, then suddenly it's a different game altogether. So just by adding, 12 more orders of magnitude, 12 more significant digits to your time delay, suddenly you can ask new questions that you just couldn't ask before. So for example, you have 4 time delays, and if the FRB were to repeat, you measure the 4 time delays a second time, let's say a year later. In that year, a lot of things have happened. The universe has expanded. Of course, the expansion change is huge, as measured in nanoseconds. So you just get an instant snapshot of the universe expansion. A much bigger effect is the transverse motion of the lens itself that will change the time delays. But it turns out that transverse motion only is a 2-component vector. So it eats up 2 of the 3 independent time delays that you've measured. So in principle, there is information left to measure something about the universe. And we have a paper that goes into this discussion into more details. And of course, it's not without complications that these macro lenses will inevitably be split into micro lenses, which again will all be observable through these coherent effects. So you will start to measure the mass function. So even if this doesn't work, you'll still measure the mass function of stars and the lensing galaxies. So a lot of things you can learn that it makes lensing of coherent sources a very different game than regular gravitational lenses of a quasar. Again, they're exciting. I can go on for hours about the interesting tools that one has, that one can use to measure, to calculate the wave effects, the imaginary images.
3 minutes remaining. Sorry to interrupt.
Yeah, thank you. That one can use Picard-Lefschetz theory to try to solve these things. That's, for example, when we have microlensing by planets, it turns out planets are of a size where the wave optics actually fully matters and changes what you actually measure. And I'm just going to jump over that. Here I just want to give a paper that Robert Main wrote that demonstrates plasma lensing of the Black Widow pulsar 1957 plus 20 when the plasma wind of a brown dwarf companion causes strong lensing of the FRB itself. And some of the features may relate to phenomenology that FRBs exhibit. So you can see here it's measured in the 300 megahertz band. Some FRBs are also measured in that band. And you can see strong magnification of the pulses as a function of time and frequency that changes with time and changes with frequency. You can see a downward marching series of caustics of the lens that are magnified factors of 10 over what you normally see. So this is a concrete example of a coherent source that undergoes wave optics plasma lensing, from which we can try to understand things in a more controlled environment that may be a handle to learn more about FRBs. So that brings me to the summary of what I'm trying to advertise here. It's mostly advertise some concept of using coherence, is that the wave optics changes the nature of what one can observe. So one should think more ambitiously. So these FRBs, I think, are a game changer. So they're not just yet another blip on the sky of objects that may be far away and localizable. They may be the most precise thing you can measure, period. 10 to the minus 26. There are not many things you can measure to that kind of precision. That they are describable, they're calculable. It requires some of these things require new tools. Some of them you can use existing iconal tools. So it's a good opportunity to apply tools developed in different fields. Quantum mechanics has been a very successful, of course, toolbox on which one can draw that describes how wave packets propagate. And I want to advertise the applications that have been very successful on the Crab pulsar, to think whether we could have similar phenomena for FRBs, because many of them are also scattered. And I'm speculating here based on a sample of one, for which we have observational evidence that they are also scattered very close to the source itself and not somewhere halfway along the path. But these are questions we can answer in the near future with existing data. It's just a matter of analyzing the right way. If we can find similarly drifting narrowband pulses, maybe we can measure Lorentz factors of the emission. And whether or not they lens, there was debate about that. It's all things I think we can answer from the plasma lensing properties. And I'm just going to end on something I didn't actually get into, that VLBI measurements of FRBs allow us to probe these certainly plasma lensing effects and also gravitational lensing, if you were to see them, much more precisely and use them in a coherent way. Thank you.
Thanks, Lupi, for a very interesting talk. If you have questions for Yuli, please drop them into the Q&A section. So I do see a few questions here. So the first one is from Mohit Bharadwaj, who's asking, is there any smoking gun evidence of plasma lensing in case of fast radio bursts?
Well, Main et al. Demonstrate that FRBs scintillate, so that's by plasma. So I think this is, I think I had a reference, Robert Main's paper from a few days ago. I don't think there's any ambiguity that they clearly scintillate. No other extragalactic object scintillates diffractively like that. So this is measured. This is not a matter of debate. It's a matter of measurement. And yeah, I think that settles the question.
Okay, we have another question from Zoawar Vadia Singh. We're asking, are FRBs really going to be competitive for cosmological parameters and lensing studies compared to Einstein telescope / Cosmic Explorer / LISA? And then they ask, those black hole mergers are also coherent with more information in the waveform.
Well, it's a very different kettle of fish. Indeed, black hole mergers are also coherent waveforms that can do a lot of interesting things. Just keep in mind, we have FRBs already that haven't been analyzed coherently, or not very often yet coherently. So it's a matter of things we can do today. All these other experiments listed are futuristic. And no, I'm not saying one should stop doing the other experiments. I'm saying one should look at the data we have today and answer what we can with what we have.
Thanks for that. Next, we have a question from Ron Akers, who's saying, great stuff, Yuli, but we still need to discuss the degree to which scattering will destroy some, but not all of the coherence effects.
Yes, I'd love to discuss, but I think it's even more important to measure this. This is, I think, a matter of measurement. There's so much data, there's so many FRBs that are scattered. And I think even Ron has access to data that is scattered that, to my eye, looks scintillating. I think it's a matter of analyzing it and measuring modulation indices of these things. So I think it would be great to, by discussing, meaning actually, let's go over the data and just see what it tells us.
Awesome. We'll take one more question from Adam Deller, who's saying there has been talks previously about how differential scattering along different line of sights are gravitationally lensed FRBs. Can you comment on whether you think that will destroy the coherence?
Well, certainly for certain parameters of scattering, that'll completely destroys the coherence. I don't think that's there's any doubt about that, especially with these long time delay. If you have a lens time delay of a few months, splitting of arc seconds, it doesn't take much scattering to make that impossible. But the positive note is that as you go to higher frequencies, scattering becomes less and less important, and FRBs have been detected up to 8 gigahertz. And of course, it's the repeating for lensed ones. You get to see it, repeat. So if you have good hints if you do have an instantaneous mapping, for example, with these VLBI localizations in CHIME outrigger and chord. Hopefully, you'll know immediately if this thing is sitting right on top of a galaxy that's likely to be lensed. And then you can just look at it with high frequency telescopes and look for the lensed images that are not scattered. So I'm hopeful that observing strategies can allow you to bypass scattering that could, of course, otherwise be a big problem.
Very interesting stuff. Thanks, Yulipen. I think we should move on to next talk now. Thank you very much.
Thank you.
The next talk is a recording, and the speaker is Robert Lilow. And they will be talking about a new measurements of the Hubble constant using fast radio burst. And I'll encourage, if Robert or their collaborators are online, please let us know so that we can promote them to panelists and they can answer questions. Thanks.
Hi everyone, my name is Robert Liloff. I'm a postdoc at the Technion in Israel. And before I start, I would like to thank all the organizers for creating such a great conference and also for giving me the opportunity to give this talk. I have to say I'm still very much a FRB novice. I'm learning a lot of things during this conference. I'm first and foremost a cosmologist, and together with my two collaborators, Stefan and Robert Reischke, a bit more than a year ago, we got really interested in using FRBs as a means of probing cosmology. And I want to talk about one of the projects today, namely how to use FRBs to measure the Hubble constant. Given the audience of this conference, I'll spare you all the basic details about FRBs and directly focus only on those properties which are relevant for its cosmological application. Namely, first, they are luminous enough to be visible at cosmic distances, so allowing us to cover large redshifts as well as volumes. And the dispersion measure probes the line of sight integrated electron density, and via this gives us access to cosmological properties. Now, I split the DM in the usual way into a contribution from the host where the FRB was emitted, the large-scale structure along the way, as well as the Milky Way contribution. Now, the latter can be modeled with models that have been calibrated against galactic pulsars, and that's also what we're using here and subtracted from the observed DM. Now, it's more tricky with the host contribution, of course, since it is supposed to scale with 1/1 plus the redshift, first and foremost. But beyond that, its characteristics are way more uncertain. For example, there could be additional redshift dependence due to host evolution. Then the typical value of DM host will depend on the type host. Then, of course, the position of the FRB source within the host halo also makes a huge difference. So given all these uncertainties that we still have, we do a very simple assumption here and approximate it just by some mean value plus a Gaussian scatter, where for the values we assume a Milky Way-like host galaxy. And last but definitely not least, we have the large-scale structure contribution, which contains all the cosmologically interesting information, and at least for those FRBs from high redshifts, is the dominant contribution, which is one of the reasons why FRBs have a much higher signal-to-noise than most other cosmological probes, such as weak lensing and galaxy clustering for the same number of sources. So let's focus on the large-scale structure contribution to DM, which is given by the line of sight integral over the electron density in the IGM. And via this electron density, we get access to a number of different cosmological properties. So let me just go through them in a broad fashion. First of all, depends on the global fraction of baryons. It's also sensitive to the fraction of baryons in the IgM. Then, of course, the ionization history. But you can also go beyond the mean electron density and look into dependence on density fluctuations by probing the correlation function of the dispersion measure. So in this case, the BE here is the bias of the electrons relative to the matter density. We've also looked in other projects into these angular correlations of the DM, but that's not the focus today. The focus today is on probing the expansion history, where the dependence actually comes into this dependence of the distance L to the redshift in this line of sight integral. So, but before I go into detail of how to explicitly constrain the expansion history of FRBs, let me just say a few more general words about probing the expansion rate, the Hubble rate H, as a function of Z. As usually, I describe it here as its value today, H naught, and the expansion function E of Z, where we assume standard flat lambda CDM shape of the expansion function parameterized with the matter and dark energy density parameters. And to constrain H, constrain Hubble, we need some form of distance redshift relation for whatever type of probe we have. So call this D of Z and just give a very abstract expression here. Of course, it depends on the value of H naught and the integral over the inverse expansion function. But beyond that, there will be some general kernel F of redshift, which the specific form of which depends on the type of distance we're looking at. For example, is it the luminosity distance? Is it the angular diameter distance? Or is it some different, more effective distance? Then you just need to observe some redshifts and the according independent distances to constrain H. Normally in cosmology, getting the redshift is the easy part. Not so much for FRBs, but normally it is. And the distances are quite tricky. And what you need for distance is some physical scale that they're anchored on. Broadly speaking, there are two categories of these distance scale anchorings in Hubble measurements. First of all, there are the early type measurements, where the physical scale enters the sound horizon, or equivalently, the baryonic acoustic oscillation scale, imprinted during the time of recombination. And so this is, for example, the scale that effectively enters into any constraints that you get from the CMB, like by the Planck machine. On the other hand, you have a variety of late type measurements where the distance scale comes into play due to a combination of a local distance ladder together with standard candles like supernovae or the time delays of gravitational lenses or other means of some standardized quantity. Now, in recent years, it has been found that there's a rising tension between these early and late time measurements, which the order of 4 sigma or larger, depending on the details of your comparison. And that could be either due to systematics or to new physics or both. And any type of new independent measurements of Hubble would, of course, be extremely helpful in trying to pinpoint the reason for this tension. And this is exactly where we want to use FRBs, as also had been suggested beforehand by Qiao Wu et al., who also gives a talk in this conference. Now, what we do is, in this case, we use the mean value of the large-scale structure dispersion measure contribution as a function of that as such an effective distance measure. So essentially, we use the Marquardt relation as a distance redshift relation, and I've just written it here again and spelled out all the cosmic parameters. Now, for our analysis, we can assume the IgM fraction and the ionization fraction to be approximately constant, and assuming and using these standard values for those. But after fixing those, we still have to deal with the fact that there is a complete degeneracy between H naught and the baryon density parameter omega b for any of those measurements based on FRBs. So we need some type of prior on the baryon density to actually constrain H naught. So there are a couple of ways you can do this. You can either take prior on the combination HB times H naught squared, which you can get either from the CMB or from Big Bang nuclear synthesis, or you can take direct prior on omega baryon, which you can get, for example, from the gas fractions and clusters. Then, of course, we also have to take into account the scatter in this large gas structure DM contribution, which we, for simplification, assume to be linear in redshift, with spanning this range of values, which we took from Jaroczynski 2019, based on the illustrious hydrodynamical simulation. And then, once we combine all of these with a set of FRBs with known host redshifts, we can constrain H0. So, a publication, a set of FRBs with known host redshifts available were these 9 points shown here. We plot the large gas structure DM over the redshift, reaching redshifts of nearly 0.7. And you can see they nicely follow the black line here, which describes our expected model. The error bars here contain 3 contributions: the uncertainty in the Milky Way model, the scatter that we assume for the host, as well as the scatter that we assume for the large gas structure contribution. Consider 2 types of samples, either all 9 of these FRBs, or just a so-called gold sample, these red points, where we exclude the black ones because they have larger uncertainty on the host identification. And here show the results for our H0 constraints. So in this analysis, since we only have 9 data points, we use a fixed value for the combination omega baryon times H0 squared that we get from Planck CMB measurement. And for the host contribution, we assume these values for the mean and scatter. And then the colored lines here show the H0 PDFs that we get for all the individual FRBs. You can see that the low redshift ones tend to be broader and have less constraining power. That's because they are more dominated by the scatter in the host rather than the cosmic signal. But if you combine all of these points together, you get the thick black line. And if you only combine the gold sample values, you get the dotted line. As you can see, the difference is rather marginal, and that's because the 3 points that we excluded from the gold sample have rather low redshifts. So all the really highly sensitive high redshift FRBs are actually also in the gold sample. For comparison, I'm also showing here in blue the result from the CMB, from the Planck mission, of the late time measurement fraction, and from the early and from the late time measurement fraction, the most prominent contribution by shoes, so a combination of distance ladder, Cepheids, and supernovae, which are 2 of the results of the largest tension between each other. And as you can see here, our results are on the positive side, perfectly consistent with these previously found values. But of course, since we only have 9 FRBs, our error bars are still quite large, order of 16% error. So we can't really distinguish between these 2 results. However, of course, in the near future, we expect to have many more FRBs, also with known hosts, hopefully. And then we can definitely push these error bars down. So we did a forecast. So first of all, what I'm showing here is a very simple, naive extrapolation just of the previous error bars, assuming the scale with a square root of a number of FRBs, just to get a feel of what is possible. And as you can see here, if we assume if we have a couple of 100 FRBs with known hosts, we should be able to get down into the 1 or a few % precision regime, so we could become competitive with the pre-existing measurements shown on the previous slide. Now, of course, if we get down to those high precisions, we have to worry more about potential biases in this analysis, especially due to unknown properties of the host. For example, if we assume a different value for the mean host contribution, this systematically changes our estimate for H0. But luckily, we can relax some of these assumptions as soon as we have a couple of 100 FRBs. And this is shown here in a proper forecast, where we generated 500 mock FRBs, whose redshift distribution corresponds to the one of the observed FRBs today. We can relax the assumption for those by assuming, not assuming a fixed value for the mean host contribution, but leaving this as a free parameter, which we can do because the redshift dependence of it is different from the one of H0. So this breaks the degeneracy. We also leave omega meta free. And instead of fixing HB omega b h squared to a fixed value, we allow for wider prior taken from Big Bang synthesis. And then if we run our analysis, these are the results that we find for the three parameters H, omega n, and the host contribution. And as you can see, even though we introduced these extra 2 free parameters with 500 FRBs, we still are able to get really decent error bars on H0 of the order of 3%. And we also accurately reproduce our input mock value for Hubble. And with this, I'd like to come to the end. Let me just summarize my talk. So the dispersion method of FRBs, as it probes the electron distribution, gives us access to cosmological information, both via its mean as well as its correlations over the sky. And it's a particularly powerful probe due to its high signal-to-noise compared to other cosmological probes and the very large accessible volumes. So with the currently available FRBs with host identification, we get the result of 62 plus minus 9 kilometers per second per megaparsec, so order of 16% error, which is still rather large. But very soon, this should hopefully change. As soon as we have a couple of hundred FRBs with hosts, we should be able to get high precision independent constraints on H0. But of course, as soon as we have more FRBs, much more will be possible, which I didn't have time to talk about today. But let me just give you a small teaser. So for example, in 2 other projects, we checked what you can do with a few thousand FRBs, but without assuming any host identification, and looking at their correlation function. And then it turns out that you can actually get really competitive results on prime monogonality and the equivalence principle, for example. So with this, I want to come to an end, and I'm happy to discuss, of course, about any of these topics and other possible applications of FRBs in cosmology during this conference. Thanks a lot.
Thanks, Robert, for a very nice talk. I don't see Robert online, so maybe if one of their collaborators are present, they can answer a few questions. We have one question from Matthew McQuinn, who are asking, we probably don't know the fraction of baryons in stars to better than a couple percent. I think no one's online from this collaboration, so maybe I'll post these questions to Slack, and when they are up, they can answer the questions. Okay, so moving forward, next talk is a live talk from Qiao Wu from Nanjing University, and they're going to tell us about an 8.8% determination of the Hubble constant from fast radio bursts. All yours, Qiao.
Oh, okay. Thank you. Can you see my screen?
Yes.
Oh.
Thanks.
Hello, everyone. I'm Qiao Wu, a PhD student from Nanjing University in China. It's a great honor to introduce my recent work here. The topic of my report is 8% determination of the Hubble constant from localized fast radio burst. And here are my collaborators. Now we all know that the universe is expanding, and one of the most important questions in cosmology is measuring the expanding rate of the universe, which is the Hubble constant. People have used the different methods to measure Hubble constant, measuring the luminosity distance of nearby stars, and establishing a cosmological ladder is a traditional measurement method. In this plot, blue stars correspond to the measurement of Hubble constant in the local universe with calibration based on CFAS. Another remarkable method is to use the power spectrum of cosmic microwave background to measure Hubble constant. In this plot, the red dots refer to derived values of Hubble constant from the CMB, assuming a lambda CDM model. However, with the improvement of observation accuracy, the measurement deviation under the 2 different methods is larger and larger. and the difference is up to 4.4 sigma now, which is also called the Hubble tension. Now, measuring Hubble constant with gravitational wave has become a more reliable method. The green courses are direct measurement of Hubble constant with standard series. Now, one urgently needs new distance indicators to test the Hubble tension. As a new cosmological probe, FRB can be used to measure Hubble constant. Firstly, I will give a brief overview of FRB here. FRB is a bright radio transient source with cosmological origin. FRB is very special that has very short duration. And the dispersion measure value of FRB is very huge, that far exceeding the DM value contributed by the Milky Way. It has a very high brightness temperature, which means that its radiation mechanism should be coherent. And the current research showed that some repeating FRBs have long-term periodicity, including FRB 1809-16 and the FRB 1211-2. With the search of CHIME with large field of view, more than 600 FRBs have been found. This figure shows the position of all the FRBs in the sky maps. For FRB, a very important observation is the dispersion measure value, which is defined as integrated Coulomb density of free electrons between observer and the source, as this formula shows. The most significant factor affecting DM is the value and the distribution of electron number density. As shown in this figure, when a FRB reaches to the Earth, it will pass through the host galaxy, intergalactic medium, and the Milky Way. Obviously, the observed DM mainly comes from the contribution of these three parts. Next, I will introduce how to determine the DM values of these three parts. The first is the contribution of Milky Way, which divided into two parts. The interstellar medium and the halo. The contribution of interstellar medium can be divided according to the galactic pulsar model, NE 2001 model and the YMW16 model. While the contribution of the halo is between 50 and 80. Here we assume 50. For the contribution of the intergalactic medium, so-called IGM, the average value of DM IGM can be expressed as the relationship with this with redshift. That is in this question. Here we express the Hubble constant separately, and the other can be given by other observations. We can use this relationship to measure Hubble constant with FRB. The last and most difficult to handle is the DM contributed by host galaxy, because the properties of host galaxy of FRB are different, and the FRB is located in different positions in the galaxy. There are significant differences in DM host between different FRBs. Actually, I used to measure Hubble parameters with FRB before. In the flat number CDM model, the expression of Hubble parameter is shown by this formula. We know that there is a dependence between the average DM-IGM and Hubble parameter. Therefore, as long as we know the redshift and DM value of FRB, we can measure Hubble parameter according to the dependence. Since the number of localized FRBs known at that time was very small, we simulated 500 FRBs using Monte Carlo method, as shown in this left figure. The DM and the redshift of FRB are shown here. The redshift range is assumed 0 to 3. The results are shown in the right figure. The red line here is a theoretical value, and the blue points are Hubble constant, Hubble parameters calculated according to FRBs. We found that the maximum deviation of Hubble parameters from standard nominal CDM model is about 6% at relative 2.4. And the p-value of case test is 0.23, which confirms the internal consistency of this simulation. This result showed that it is effective to use FRB as a cosmological probe to measure cosmological parameters. That also prompted me to measure the Hubble constant with FRB when the number of localized FRBs are enough. However, a problem that needs further consideration is how to get more accurate DMIGM and DM host. For different FRBs, DM host will be different according to the properties of host galaxy and the location of FRB in the galaxy. Here, we assume that DM host satisfies a log-normal distribution, as shown in the above figure on the right. This is the DM host distribution with a ratio of 0.2 in June 2020. As shown, we take this distribution to present the DM host. The other is the distribution of DMIGM. Because the electron number density and the line of sight direction in different FRB propagation paths are different. The DMIGM value between different FRBs vary greatly. In this paper, we consider such a distribution obtained by TNG simulation to describe DMIGM. As shown in the lower right figure, this is a probability distribution of DMIGM at different relationships given by June 2021 through simulation. For detailed introduction, please refer to Wang's docs. Once we have these two distributions, we can give the likelihood function and then calculate Hubble constant through Monte Carlo macro-chain analysis. With the improvement of the observation, more and more FRBs are located now. Here we list 14 localized FRBs. The table on the left shows the FRB name and the redshift. This plot on the right shows the DMIGM value and the redshift after deducting the Milky Way and DM host according to distribution. The blue line corresponds to DMIGM results from the TNG 300 cosmological simulation, and the purple shaded area is a 95% confidence region. The red line shows the model. It can be seen that basically all the observations that are within this range. And then we use the MCMC analysis. And here we show the results of our measurement of Hubble constant, which are shown in this figure. The black solid line shows the probability density distribution of Hubble constant, while the area between the two green vertical lines show the results at 1 sigma confidence interval, and the blue vertical lines correspond to the Hubble constant derived by GW17 or A17 at 1 sigma confidence interval. The orange and yellow region correspond to the 1 sigma uncertainty range of Hubble constant derived by supernova and CMB respectively. It can be seen from this figure that the accuracy of measurement of Hubble constant is relatively better than the measurement of GW17 or A17. Although it's not as accurate as the measurement of Hubble constant by CMB and supernova, it is mainly due to the insufficient amount of data. From this figure, we can see that the limit result of FRB is closer to the result of CMB. However, the current measurement accuracy cannot completely exclude the result of supernova. Moreover, according to the current development trend of FRB observation, we expect more localized FRBs in the near future. As I said before, FRB observation is in a period of rapid development now. In order to predict the ability of FRB to measure Hubble constant, we use Monte Carlo method to simulate 100 FRBs with a redshift distribution similar to gamma ray bursts. The simulated points are blue points in this figure. Next, we adopted MC analysis to measure Hubble constant. Here is the results to constrain Hubble constant. And the error is only 2.6% in 1 sigma confidence region. This error is small, so it is also enhances our confidence in measuring Hubble constant using localized FRBs. If we have enough localized FRBs, we can give a good limit to Hubble constant, so as to alleviate
3 minutes remaining.
Okay, thank you. The Hubble tension. Of course, the key point is the number of the localized FRBs, which requires better observation equipment and technology. At present, the telescope we use to locate many, including VIBI, DSA-10, SCAP, VIA. It is believed that with more accurate positioning of this telescope, we can take a breakthrough in the number of localized FRBs. Next is my conclusion. The Hubble constant derived by 14 localized FRBs is 64.67 plus 5.62 and minus 4.66 with 8.7% uncertainty. The Hubble constant derived by 100 simulated FRBs is more accurate, and the uncertainty is 2.6%. FRBs can provide a promising and novel way to measure Hubble constant, which is of great significance to the study of cosmological expansion and alleviate the Hubble tension. More localized FRBs are needed for cosmological application in the near future. And thank you for your listening.
Thanks a lot for a great talk. If you have questions, please post them in Q&A, and I can see some questions popping up. So the first question is from Zovar, who are saying that, isn't assuming a DMZ relation a bit circular? For instance, if you needed to reproduce the DMZ relation from the first principle simulation, you would need a cosmology and H0.
Yes. When we use the simulate, do the simulation, maybe there has this question, but when we have the FRB data with DM value and redshift, we can use this to calculate the Hubble constant, and we don't need the Hubble constant, and we can derive this. So with the real data, it can we don't have this problem.
Okay, thanks. We have another question. You want to add something to that?
I answered no.
Okay, yeah. So next question we have from Ron Akers, who's asking that the distribution and redshift dependence of intrinsic host DM will be a problem. Can the lower limit, 0, for example, for host DM provide a strong constraint when using this method?
Maybe I didn't. Maybe it can give a strong constraint, but I didn't try it. I didn't. Yeah.
The next question we have from Ray Lu, who is asking, have you modeled the DM distribution contributed by the local environment of FRB progenitors, such as star-forming regions or supernova remnants? that's obviously non-negligible for current localized repeaters. And then they ask, do you think if the precision of Hubble constant you measured can be enhanced by considering this distribution?
Oh yeah, actually, I didn't the DM host distribution is conferenced by June 2020, and I don't know whether they consider the star formation regions or supernova mates. But I think if consider more precise and the process of measuring Hubble constant can be improved. Yeah.
Okay, and lastly, Matthew Bales is asking, I suspect that the FRBs with very little scattering are unlikely to have much anomalous excess DM compared to the scattered ones. Yuli might want to comment.
Maybe I think the scattering is not very important in my work. Yeah.
Okay. Do we have any further questions for Quinn? Okay, if not, we'll move on to our next talk, which is a recorded talk again. The speaker is Stefan Heimersheim from Institute of Astronomy, University of Cambridge, and they're going to tell us about model independent constraint of hydrogen reionization with fast radio bursts.
Hello, my name is Stefan. I'm a PhD student at the University of Cambridge, and together with Nina, Anastasia, and Duncan, we have looked into hydrogen reionization and how to constrain it with fast radio bursts. You might have seen a few forecasts over the last year or so about reionization with FRBs, and in this particular work, we want to look at how to avoid the biases and the assumptions that go into the current forecasts by using a model-independent method. So in this talk, I want to convince you that indeed, we have these model-independent methods, and we can use them to get as good or even better than before constraints on reionization. To give a very brief overview of what this is, here's my cosmologist picture. The very early universe of the first few 100,000 years is very well studied by the CMB, and also the last few billion years are quite well studied by just looking at galaxies in large-scale structure. And in between, you have this period which we call dark ages or era of reionization, and we don't know very much about this. You can also see this if you look at our standard cosmological model, where we have 6 parameters, 5 of which are pretty much constrained very well, but the last one, the reionization optical depth tau, is very unconstrained. And fast radio bursts could actually provide a really good probe for this era. So current constraints go only up to redshift 7, maybe 8, mostly quasars and galaxies for the reionized fraction of the universe. But we already have some FRBs for, well, rather low redshifts, but plausibly we could get FRBs much further out than those galaxies and quasars where we would need AGN, while FRBs might be created by stellar sources that could exist much earlier. So just briefly, what do we use to do this constraint? Of course, we use a dispersion measure of fast radio bursts. And apart from the host galaxy Milky Way contribution, the main interesting contribution for cosmologists is the IGM contribution. So this is all the electrons along the line of sight in the intergalactic medium between the source and us. And of course, if you look at this kind of equation, it's an integral over the free electron density. So on the one hand, this will depend on the background cosmology here. So you see the baryon abundance omega b. You probably also saw the 2020 Macquart et al. Paper that found the missing baryons with fast radio bursts. And we also have the Hubble rate, which allows us to, say, measure the H0 parameter. You'll see 2 talks on this in this very session. And it could also allow us in the future to measure, say, the meta abundance omega m or the dark energy equation of state. On the other hand, in this equation, you have this ionization part. So this tells you how many of those baryons in the universe are actually ionized. And we know that the universe must have been neutral at very high redshifts. And we also know it is approximately ionized around redshift 5, maybe 5.5. And in between, the universe must have transitioned from the neutral to the ionized universe. Also, there's a bit of helium-2 reionization at later redshifts, but I want to focus on the hydrogen and helium-1 between redshift 5 and say 15. And the main targets we want to measure are the ionization history, so that's the ionized fraction xi as a function of redshift, and the reionization optical depth tau. So this optical depth tells us how many photons from, say, the CMB rescatter on their way to us from all those ionized electrons in the late universe. Okay, so how do we use this dispersion measure to constrain this ionized history? Basically, there's a mapping between the dispersion measure and the ionization fraction, just because the dispersion measure is simply an integral over the ionization history plus a few factors. So if we would measure the dispersion measure as a function of redshift perfectly, we could just infer the ionization history. But of course, we can't do that. We will only have a few observations of dm and z. So what we can do is you can parameterize your model for the ionized fraction. For example, you could have this very common tan-H step function model used in Planck, in WMAP, all the CMB analyses, and a few FRB papers. And there you just vary the redshift and width of reionization, and then we see what impact does it have on the dispersion measure. So you can imagine here, if we have a few measurements, we could constrain those parameters. Alternatively, we could use numerical simulations for the ionization history. So we choose astrophysical parameter and run simulations to get the ionization history. And then you could compare the respective dispersion measure to the observations and get constraints on those astrophysical parameters, and with that also on reionization. And this actually has also been done for FRBs recently. The problem with all of these methods is, what if the actual true reionization history of the universe is not included in your model? Say, imagine you have this simple step function model. If the true universe doesn't have a step function reionization, your model is going to be wrong. And actually, it can be very wrong. So we generated a bit of realistic mock data and saw if you assume a tan-H model, even though the real ionization history is not a tan-H, you can be wrong by like 10% and actually be off by a few sigma. So this can be really bad. And if you have peta parameterizations, you might get closer, but you will always have the problem that if your parameterization doesn't include the reality, you will always get some bias. And we can't be sure of that because we don't know how the real reionization history looks like. So we can't just assume some model. The question is, what do we do now? Luckily, the CMB field has already worked on this problem for the last few years, and there have been methods developed. The most recent one of which is a flex-knot method, which basically goes back to this problem of saying, okay, we have this ionized fraction as a function of redshift. We know it's 1 over here, and we know it's 0 over here. And we just put a few points in the space in between, and then we just draw the function by connecting those points, by interpolating. And that's a very simple, basic parameterization, but we can now use those coordinates of those points as parameters. We can run some MCMC chains, and you see a picture down here where you see the coordinates of those points basically give you the ionization history. Now, you might ask, okay, how many of those knots do I have to put in? How many of those points do I need to describe my ionization history? And that's a very good question. If you have too little, of course, you will be only to fit very simple histories. And this, of course, won't fit your data and will be a really bad fit. And if you add a few more, you'll probably get quite a good fit to your data. But you can, of course, add more and more knots, and you ask yourself, when do I stop? And luckily, there's also a solution for this. We can just treat the number of knots as an additional parameter of our model, i.e. we can marginalize over it or average. And what happens in practice is that these models will be weighted by the Bayesian evidence. So that's kind of the built-in Occam's razor, where if you compare models that fit the data equally well, the models that have way more parameters will be automatically disfavored. So what you see here on the right-hand side is the evidence as a function of how many knots I have for 1,000 fast radio bursts, our mock data. And you see, if I go up, add more knots, first the evidence increases. But then if you add more knots than necessary to describe the data well, the evidence actually goes down again. So you can average over all possible number of knots by basically just taking the first 10 or so knots and average all those results out. Now, in order to test this method, we do generate some synthetic data sets because unfortunately, we don't yet have very high redshift FRB observations. And for the redshift distribution of the sources, we just take the star formation rate. That seems like a plausible assumption for the moment. And we use a Beruzzi empirical approximation of the star formation rate and generate synthetic FRB sources at those redshifts. And of course, you might ask the question, can we observe FRBs this far? So currently, I think the FAST telescope should observe fast radio bursts maybe up to redshift 10 or so, and Green Bank telescope is also searching for very high dispersion measure FRBs. So the sensitivity will get there. And we will also have to localize those FRBs because we need to identify their redshifts, for which we'll probably need DSA 2000 or SKA, so telescopes with a very good accuracy in terms of localization, although adding outriggers to existing telescopes might also be a good method for this. The next step in generating our synthetic dataset after we have the source redshifts for the FRBs would of course be to calculate the dispersion measures of all the FRBs and also correctly take into account all the uncertainties on this. So the main and biggest uncertainty is here the IgM contribution, because of course the IgM is inhomogeneous, which means between FRB and Earth there might be more or less matter than whatever is the average, which means there's a bit of scatter in the dispersion measures that we get, and this can be up to a few percent depending on the redshift, and this would be in most cases the dominating uncertainty on the dispersion measure. The next biggest uncertainty in this mock data set is the redshift measurement. We assume a 10% error on the redshift determination from, say, spectroscopy or photometry. And this, of course, is an error in redshift, not dispersion measure, but it corresponds roughly to a few hundred parts per cubic centimeter, depending on at what point you measure this. And our goal here, if you have 10%, this should be fine. But if you have bigger redshift errors, this could actually be a dominating source of uncertainty. The next uncertainty is the host galaxy contribution, which of course we have no idea what it is, although we can kind of estimate what is approximately the order of magnitude. And in general, we will usually expect something less than 100 or so parts per cubic centimeter, which means this should be a subdominant source of uncertainty, as well as the observational error. If we can make a good measurement of the dispersion measure, this uncertainty of the dispersion slope would be usually much less than the cosmological error contribution. And then we add all those contributions together. So you'll see on the right-hand side our generated mock data in orange, and the green points were the original kind of exact data points without any scatter. So you see kind of how those errors influence the data. And now that we have this data set, we'll of course test our method and see what constraints can we forecast, what could we get. And this is again the ionized fraction as a function of redshift, and these orange contours now show you the posterior constraints that we get from 1000 localized FRBs. Between redshift 5 and 10 again, although as I mentioned earlier, mostly at rather low redshifts before redshift 10. And you see we get quite a good constraint at the low redshifts, so below redshift 10. And we can actually, for example, really well measure, say, the midpoint of reionization. But then over here at high redshifts, the constraints aren't that strong just because we have very, very few FRBs. Luckily, there's one trick we can use, a nice synergy between the CMB and this. And because the CMB is actually really sensitive to very high redshift ionization. So you can actually get an upper bound from the cosmic microwave background on reionization beyond redshift 15. And one big advantage of using this method, this kind of flexsort method, where you have a function for every of your data points, you can take this function and compute all possible quantities that you might need for additional constraints. So what we can do is we can take all our histories, compute what is the optical depth constraint beyond redshift 15, and then compare this to the Planck constraint, which is an upper limit on the optical depth beyond 15. And this allows us, if you look at this comparison, to reduce the uncertainty at high redshift. That's very nice. And of course, as I mentioned earlier, the other advantage of having a function as opposed to some points in ionization history space is you can take every of these functions and ask, okay, at what redshift does this sample reach the midpoint of reionization, xi equals 0.5, or maybe the start or end of reionization? And then I can look at all those redshifts and compute the posterior distributions for these as well. So that's the numbers I show you here for, again, 1000 FRBs plus the CMB constraint. Finally, we get to cosmological parameters, and here are 3 parameters that are interesting. Most of all interesting is, of course, the optical depth tau, and the other parameters that go into that we vary are the omega b over h, so the baryon abundance over Hubble constant, and the meta abundance omega m. And luckily, we find that the tau optical depth constraints are very independent of both omega B and omega M, and we can get a good measurement, a very accurate measurement compared to, say, the Planck CMB measurement. As you see in this zoomed in plot here, the dashed line is the current best Planck measurement, and the blue and orange contours or histograms are the measurements with 100 or 1,000 FRBs respectively. And you see we get already much more accurate constraints, especially the lower limit is much stronger for these FRBs compared to, say, the Planck measurement. And this does not only increase this one last parameter in our cosmological model, which is already great, but it also helps us increase other parameters in the cosmological model. For example, the primordial power spectrum amplitude, AS, is actually quite degenerate with the optical depth, tau. So if you look at the gray contour here, that's a Planck constraint, you see there's a big degeneracy between tau and AS. And if we now have, say, 100 or 1,000 FRBs, we can also improve this measurement. And a very similar relation holds true for the neutrino masses if we include future LSS survey forecasts. So with future measurements of large-scale structure, the neutrino mass determination will actually depend a lot on having a good measurement of the optical depth. So that's a field where we could also improve other cosmological measurements. And now I just want to leave you with my summary. So FRBs can indeed probe reionization. We do need localized FRBs at high redshifts. But even if we just have 100 FRBs beyond redshift 5, we can get competitive constraints comparable with the best current Planck measurements. And we can also use a very nice synergy with the CMB to help with the very high redshift inaccuracies. And we do need to avoid the biases in our current methods. So we should use something model independent like presented here. And this is of course applicable to all kinds of functional constraints, not necessarily only the reionization history. And please do send me questions in the Slack or via email, or very happily on the next live talk in 12 hours. And otherwise, also feel free to check out my source code on GitHub for all these constraints. And let me know when you have any questions. Thank you.
Thanks, Stefan. I don't see him online, but we do have 2 questions in the Q&A section. One is from Jing Liang, who's saying that, is that realistic that we can detect FRBs with redshift that can span up to 30? Another question is from Mohit Bharadwaj. He says, nice talk, Stefan. Is it possible to use unlocalized FRBs instead of 100 plus localized FRBs at redshifts greater than 5, which I doubt is possible in the near future? Please post these questions in Slack for Stefan, and when he's up, I'm sure he's going to respond to those. Okay, so moving on, we have next speaker who will be giving the talk live. Khee-Gan Lee from Kavli IPMU University of Tokyo. They're going to tell us about constraining the cosmic baryon distribution with spectroscopic foreground mapping of FRBs. Take it away.
Thanks, Shivani. So my talk today is gonna of a similar spirit of the last couple of talks. So I'm not gonna give a lot of background, but basically I first want to give credit. So basically we're working on a theory/forecast paper that I am leading, but a lot of the work is also being done by a couple of postdocs at IPMU, Metin Atta and Ilya Krikin. And we are already doing observations that I'm going to describe that's being led by master student Yuxin Huang. And a lot of the FRBs that we are studying are basically downstream from the craft localized FRBs, which were of course localized with F4 collaboration. So we are building on the fantastic work from these collaborations. So just a very quick background that we've already heard a little bit, which is, this McCord relationship that shows you the cosmic DM dispersion measure as a function of redshift, which of course last year in the famous paper basically solved the missing baryon problems by showing that all the cosmic baryons are out there. So in that sense, the missing baryon problem has been solved, but we still do not know the relative distribution. So we do not know whether they're predominantly in filaments or whether they're mostly clumped around galaxies. The gray curve here shows the kind of the scatter, the 95% scatter of the cosmic DM as a function of FRB redshift. So this basically says that there's a big, at fixed redshift, you can have sightlines that go through dense regions or going through the CGM of galaxy halos and giving rise to a large DM, or you could have sightlines that go through underdense regions and thus have a small DM. So the basic premise of this talk is given a localized FRB, we want to maximize the value of each FRB for cosmic baryon analysis by observing the foreground galaxies and large-scale structure. So I'm just going to describe the framework that we're assuming. So we've seen various versions of this plot already, but I want to, where of course the DM that you observe from the FRB can be broken down into the Milky Way component, some extragalactic component, and the host component. And I think so far we haven't seen a further breakdown, which in my case, I'm going to break down the extragalactic component into the DM IGM and what I call DM halo. So DM IGM, I'm going to refer to is coming from large scale structure that is diffuse. So the matter density is going to be less than 10. And in the business, like we will call that the cosmic web that comprises of voids, sheets, filaments, and nodes. And at the same time, you could also have DM halo where the sightline passes through individual galaxies or within a few arc minutes or virial radii of individual galaxies. So we've also seen this equation already several times where you have an integral over the matter along the line of sight to the FRB gives you the DM IGM. And today I'm going to show you that we do not have to keep this integral as a global quantity, but in fact, we can break out the integrand and measure them individually for localized FRBs. So kind of something of this spirit has already been done in this nice, very beautiful paper by Sunil Simha analyzing FRB 190608, which is a redshift 0.117 FRB, where they use the SDSS spectroscopic survey data to estimate the DM IGM and the DM halo contributions, and explain that this is probably likely due to overdensity in the IGM along the line of sight. So we would like to go beyond just one FRB and go get a statistical sample of such data sets and then use a Bayesian framework to estimate the so-called missing baryon parameters. So the work that I'm going to be presenting is building on the Henry Case 2015 semi-analytic light cone catalogs. So these are a set of mock galaxy catalogs that were built on the Millennium simulation, which I think literally everyone has seen this particular picture, which is in fact of the Millennium simulation. So these Henry Case light cones are basically, first they modified the original Millennium simulation to be of a more updated cosmology, in this case, Planck 2013. And then from that, they generated mock galaxy catalogs with synthetic photometry on top of the halos of that simulation. So on top of the light cone catalogs, we generate kind of model DMs for specific sightlines in the catalog. So we calculate DM IGM, DM halo, and DM host. Where DM IGM is parametrized by FIGM, which is a fraction of all cosmic baryons that reside in the diffuse IGM. And then there's also Rmax and F-hot, which parameterize the extent and amount of CGM gas as a function of the halo mass. So this is basically assuming that the halo gas is described by a modified NFW function. And for DM hosts, we assume an unknown fixed values for all FRBs. And of course, we do fix some random value for our mock analysis. In our framework, we assume that the Milky Way component has already been subtracted, which introduces an error that's of order 15 per cc. So we generate sightlines and calculate the DM components. And then we also generate mock galaxy data that's in the foreground of the FRBs. So we generate a list of galaxies that are within 10 arc-minutes of the FRB sightline. So these are galaxies that are possibly going to contribute to the DM halo contribution. We also assume that there's an uncertainty of halo mass of 0.3 dex in our estimation of the halo masses. And then we are also going to generate large-scale galaxy catalog that's spanning a couple of square degrees surrounding the FRB. So these are typically of order thousands of galaxies that's in the FRB field. So the bottom panel just illustrates the kind of large-scale survey data, and you can imagine random FRBs along this line of sight in the center of this cone. So we're going to use a tool that's not very commonly adopted, that's known as matter density reconstruction. So the idea is actually very simple. We are basically trying to estimate the three-dimensional matter density field in a given cosmological volume, given a spectroscopic sample of galaxies in the foreground. So we're going to use an algorithm called ARGO that was developed by Metin Atta, who's one of the postdocs working with me at IPMU. And I'm not an expert in it, but basically it's a Hamiltonian Monte Carlo method that samples, that tries to solve for the matter density field that best fits the observed sample of galaxies. So this illustration kind of gives you a sense of the idea where given a matter density field, you observe some sample of galaxies with a spectroscopic survey, and then you try to reconstruct the actual matter density field. And Metin has spent a lot of time in the past year improving this algorithm to deal with real survey effects. So just to give you a sense of the products that ARGO delivers. So the top panel shows in the dots the kind of mock galaxy sample that we have. And here in the green star is a fake FRB in our simulation. And the color scale in the background are matter density fields that are estimated by ARGO. So when I say ARGO is Hamiltonian Monte Carlo method, what it means is that it actually it samples from the posterior distribution of possible matter density fields. So we actually have thousands of matter density fields that are in principle consistent with the observed data set. So what this means in practice is that not only do we have an estimation of the density underlying the galaxy survey, we also have an estimation of the scatter. Okay, so the bottom panel shows that the kind of differential line of sight density along the path to this hypothetical FRB, and the different lines show a set of realizations from this particular mock data set. So effectively, it means that not only can we estimate the integrated DM, we also have an estimate of the uncertainty in that. So just to give you a sense for how this improves. So in most cosmic baryon analysis, so the black curve and the gray region is what I showed in the intro slide, where basically you have at fixed FRB redshift, you have a mean DM IGM value, but also some scatter. So if you're going to do cosmic baryon analysis, you're forced to adopt that gray region as your uncertainty, because for any given sightline, that's the possible range of DM that you can get at that redshift. So the red points here are random sightlines selected from the simulation box. So these are the true DM, IGM values, and the error bars are basically the constraint from after applying these algo realizations. So you can see that we are beating cosmic variance by a factor of around 3. And it gets a bit worse at the higher redshifts, but mostly because the galaxy survey that we define becomes a bit more sparse at the higher redshifts. So the next step is to try to quantify what this means for the set of model parameters that I described earlier. So basically, we're trying to build a framework to analyze the cosmic baryon parameters. So for the IGM, DM IGM component is just one parameter, which is FIGM. So for a given sightline, you just vary FIGM, and the integrated DM IGM just goes up and down.
KG, 3 minutes left. Sorry to interrupt.
Okay. And then for the DM halo, it's a bit more sophisticated because the extent and the amount of the CGM gas can vary. So basically, this is the basic likelihood that we adopt. But the first step is to do a Fisher forecast, where we simply take the scatter adopted in the previous analysis and quickly calculate the Fisher matrix to estimate the uncertainty in the parameters. So this is basically the kind of fiducial set of parameters that we think we can get with given a sample of 30 FRBs at redshift 0.1 to 0.5. So we expect to get something like a 10% measurement of FIGM. And assuming that DM host is fixed, we also expect to get something like a 15%. And for the halo parameters, we think we can get something like a 20% constraint. So how does this compare with the case where we have no information on the foreground? This is the same sample of localized FRBs. On the left, we have the foreground spectroscopic data. And on the right, we have the case where you have no spectroscopic data. So you can see there is a dramatic increase in the constraints that we have. We are also building the likelihood analysis framework. For now, it's not working very well. It's of same order of magnitude as the Fisher forecast, but it's not very precise at the moment because the errors are quite non-Gaussian. So basically, we are now in the process of actually observing foreground fields with the AA omega spectrograph on the Anglo-Australian telescope in Australia. So the goal of this survey, which we're calling Flim Flam, is to observe something like 30 FRB fields, which is what I just forecasted for. And we actually began observing last fall. And the basic survey design is to target each FRB field with multiple visits in a single 3 square degree pointing. We are trying to have a simple and clean magnitude limited selection to allow a good estimation of the selection functions. And to give you a sense for what the observational requirements are, we're for a redshift 0.3 FRB, we would have a R magnitude of 19.8 selection, which is the same at the gamma survey, which requires something like 15,000 to 2,000, 1,500 to 2,000 galaxies per field, i.e. about 1 night of observations. So below here, I'm showing you some very, very, very preliminary data on FRB2021 that we are going to start analyzing soon. And of course, we also need intervening galaxy observations that are going to be led by a team from UCSC and PUC Valparaiso, led by Simha, Tejos, and Francesco. I'm out of time, so I'm just going to flash this so that you can pause the video later. But basically, I think this method is kind of like MSG, where you add it to any kind of analysis, is going to make it better. And I'm just going to leave my summary up. Thanks.
Thanks, KG. Do we have questions for KG Lee? Please post them in the Q&A. I see one question popping up. So Adam is saying, nice talk, KG. I think the assumption of a single fixed FRB host DM contribution is probably going to be quite problematic limiting. Do you plan to journalize this to allow for a distribution of FRB host contributions?
So basically, the answer is basically yes, because we are basically, of course, we can introduce uncertainties in a lot of the elements in our framework. So for example, I guess it was one of the bullet points here, which is that, for example, there are some FRBs where there are estimates of the DM host, so we can even integrate those. We can even integrate those estimates into our framework for individual FRBs, and then combine the likelihoods from the ensemble.
Thanks for that. We have time for one more questions. I can see Ron Akers is asking, it would be sensible to make FRB search observations in field where you have mapped all the foreground. Is this coordination being done?
Well, basically, there are all sky spectroscopic surveys, but they typically go out to redshift of around 0.1, which is why in 1906-08 they could just grab the Sloan sample and basically do this kind of technique. Beyond 0.1, there are no all sky surveys publicly available. DESI is going to try to do this for the Northern Hemisphere. So you can wait 5 years and wait for DESI to cover the fields, or we can apply for time on the AAT and do it now, which is what we're doing.
Thanks for that. And thanks for the great talk, KG. Very interesting. So next talk we have from Masoud Rafiei-Ravandi from Perimeter Institute, and he's going to tell us about, it's a live talk. He's going to tell us about probing the large scale structuring of fast radio burst with the CHIME FRB catalog. Take it away.
Hi, everyone. Thanks for having me today. My name is Masoud Rafiei-Ravandi, and I'm a PhD candidate at Perimeter Institute working with Kendrick Smith. I'm also a member of the CHIME Fast Radio Burst collaboration. In the next 15 minutes, I'm going to talk about fast radio burst from a cosmological perspective. As you can see, CHIME is a big collaboration with teams across US and Canada. And this work has been a team effort, and I'm going to share with you some new results, which we recently published. As most of you know, I'm sure, fast radio bursts are single or repeating flashes of radio signal without non-extragalactic origins. Like pulsars, FRB emission is dispersed as it passes through cold plasma along the line of sight. And the dispersion delay has a known frequency dependence. It's frequency to the -2. And the prefactor is what we call DM. It's a definition. And it's determined by how much electron is along the line of sight. So basically, it accounts for the contribution from Milky Way, intergalactic medium, and a host, which is completely unknown. Last time I checked, there were about 600 FRBs discovered with a bunch of repeaters and about 15 localized to their host galaxies. And these numbers just show how little we know about FRBs. And we need to use experiments to learn more about these sources because they can be used, perhaps they can be used as cosmological probes. So there are two main questions about FRBs. The first one I would say is what's the nature of FRBs? And the next one is, can they be utilized as cosmological probes? And I think in this session, we are trying to answer the second question, but this talk also sort of touches the first question as well. I should mention that once a DM is measured for an FRB, we have an upper bound on the redshift value of the FRB source because the host DM is completely unknown. Bright FRBs, according to the recent CHIME FRB results, are distributed randomly at a rate of about 1,000 per day over full sky. And out of about 600 FRBs, there are about 24 FRB sources that are repeating over long time intervals. They sporadically emit radio signal. Multiple radio bursts are emitted by the same source. And about 15 FRBs have been localized to their host galaxies, mostly by ASCAP. And we know that most of the known FRB sources have been discovered by CHIME FRB, as you can see in the plot below. In the plot, I'm showing the new FRB catalog, like the first FRB catalog by CHIME FRB. And triangles show you the repeating sources in the sky. So CHIME was originally designed for 21 centimeter cosmology, but it turned out to be a fantastic FRB detector. Thanks to its large field of view and a huge bandwidth, it can detect a few FRBs per day. CHIME FRB is a state-of-the-art search engine, monitors the sky in real time. It has a millisecond time resolution and 16,000 frequency channels. And it has found about more than 1,000 FRBs to date. Our first catalog containing 535 FRBs has been published recently. And we also published 3 companion papers, as you may know, with the catalog. And the focus of this talk is on FRB galaxy cross correlations. And before I get to that, I would like to show you a timeline for CHIME FRB. Back in 2014, we had this small version of the full CHIME array, which we call it Pathfinder, and we were experimenting with the design of the instrument as well as the software, because as you know, CHIME is a software telescope, and we spent a few years just developing software for this experiment. Back in 2016, for example, in particular, I was mostly involved in removing RFI from the data from the Pathfinder telescope. And the software for CHIME has been written by a large team of researchers across Canada. In 2017, we got our first flight, and I would like to remind everyone that at the time there were about 50 FRBs discovered, including 1 repeating source. And since then, CHIME has sort of revolutionized the field by discovering hundreds of FRBs and tens of repeating sources. The focus of this talk, as I mentioned earlier, is on FRB galaxy cross correlations, which we formalized back in 2020, and we forecasted in a paper with my supervisor and Qiao Masoud. We formalized and forecasted on the cross correlation, and the new data based on the new FRB catalog has been super useful for analyzing the actual cross correlation signal and finding and detecting the signal in the real data. And so I would like to, before I get started, I would like to give you a background what I mean by FRB galaxy cross correlations. For FRB arrays with high angular resolution, with typical angular resolution of about 1 arcsecond, we can associate FRBs directly to unique host galaxies so that we can measure the redshift. But CHIME angular resolution is a few arc minutes and it's not sufficient to make direct host associations. But it can still be useful for associating FRBs and galaxies statistically. So intuitively speaking, there will be an excess probability of finding FRBs in the vicinity of galaxies. And to be more exact, we compute the FRB galaxy cross power spectrum, the angular cross power spectrum, which is a Fourier space statistic as a function of the angular wave number or multiple. And in the next few slides, I'm going to describe what this statistic is, this CLFG, and F stands for FRB, G stands for galaxies. So angular cross power spectrum is a function of angular wave number. And you can think about angular wave number as 1 over the scale, the real scale on the sky. And any deviation from 0 quantifies the strength of FRB galaxy correlation. So intuitively, a harmonic space correlation at a wave number L corresponds to a real space angular correlation at separation angle pi over L. In the left panel on this slide, I'm showing you an example, a cross correlation between a galaxy population in a narrow redshift band centered at redshift of 0.4 with an FRB population with a median FRB redshift of 0.8 and an angular resolution of 1 arc minute. The function itself, the angular cross power spectrum, has two main terms. So one is the two-halo term, which you can think about it as the correlation between FRBs and galaxies in two different halos. And the other term is the one-halo term. And you can think about it as correlations between FRBs and galaxies inside the same dark matter halos, as shown on the right panel. And so the one halo term measures the correlation on a small angular scales, as you can see in the left panel in blue. And the two halo term measures the correlation between FRBs and galaxies in two different halos, as can be seen in green. And this correlation, or this two halo term correlation, arises because both FRBs and galaxies have to sort of correlate with the linear density field in our cosmology. And so our aim here is to measure this correlation function in the Fourier space and see how that correlation can be useful in understanding FRBs. So before I get started on the analysis part, I would like to summarize the results that we have obtained so far. These results are based on the CHIME FRB catalog 1. Just to summarize, we find a statistically significant cross-correlation between our FRB sample and galaxies in redshift range 0.3, between redshift 0.3 and 0.5 in 3 galaxy surveys. The level of cross-correlation is consistent with an order 1 fraction of our FRB sample being in the same dark matter halos as galaxies in these surveys. And in addition, we find a statistical evidence for a subpopulation of fast radio bursts with large host DMs, and by large, I mean host DMs of around 400 PCC. This is intriguing, given that we haven't seen such FRBs in direct host galaxy associations, which typically have, which typically exhibit DM hosts of around like between 50 to 200. We show that this large DM host contribution can be explained by a small population of FRBs near the centers of massive halos. Before I get into the analysis, I would like to show you the data that we worked with. On the FRB side, we have the FRB catalog. Our sample, as I said, it's the full sample is 535 FRBs, but we only count the unique events in our sample for this cross-correlation studies. So we have 489 unique events, and we exclude 43 low SNR bursts from repeating sources and 3 side lobe detections, just because side lobe detections tend to have less accurate localization. Using the real FRB sample, we also generate mock FRB catalogs and random FRB catalogs by randomizing right ascensions while keeping declinations fixed. And we use mock FRB catalogs for assigning error bars to the angular cross power spectrum. Randoms are used to make overdensity maps like the one that you see on the left panel in this slide. On the right panel on this slide, I'm showing you the FRB, the number of FRBs as a function of extragalactic DM, and each colored line shows you the fraction of those FRBs covered by each galaxy surveys that we used, and I'm showing you in the next slide. So these galaxy surveys that we use actually 5 galaxy surveys. They don't cover the entire sky. They have their own masks, for example, the star masks, like galactic plane masks, and so on. And so our FRB sample has partial overlap with these galaxy surveys, and these galaxy surveys cover a wide redshift range from redshift 0 to 1.4, and they are excellent candidates for doing cross-correlation studies, just because if you notice in the previous slide here, the extragalactic DM for our FRB sample peaks at about 500. And if we assume that the host DM contribution is negligible, then you would expect to see a cross correlation between our FRB sample and these galaxy surveys at somewhere around redshift 0.5. And so we cross correlated these overdensity maps of galaxies with our FRB overdensity map, and we got some exciting results here. I'm briefly summarizing the results that we found. We find a statistically significant correlation between our FRB sample and galaxies in the redshift range 0.3 and 0.5 in 3 galaxy surveys. The first one is WISE cross-matched with Super Cosmos. The next one is DESI BGS, and the last one is DESI LRG. We don't find significant correlation with the other two galaxy catalogs. And I should mention here that we adopt a redshift cut for our galaxy catalogs. In other words, the angular cross-power spectrum, which I mentioned earlier as a function of angular wave number, is now a function of two variables. One is the angular wave number, the other one is redshift endpoint. So here, for example, in the top panel, I'm varying the minimum redshift cut for the WISE Supercosmos galaxy catalog. So my angular cross-power spectrum is now a function of angular wave number, as well as zoom in or minimum redshift cut. But in this plot, I'm just showing you a fixed zoom in, just because it's easier to look at the plot. By varying the redshift endpoint, we can basically constrain the correlation between our FRB sample and galaxies in the redshift space. On this plot at the top, I would like to go over the lines, what I mean by each data point here. So these bands in orange, these are the band powers. They are basically the CLFG, the angular cross-power spectrum, based on the cross correlation of our FRB over density map and the galaxy map with this redshift endpoint. The blue line is the galaxy auto-power spectrum, and the dashed line in blue is the galaxy shot, the shot noise term. And we also have a fit to the angular cross-power spectrum to these band powers. And I will show you, I will describe what this fit means at a fixed characteristic scale in a moment. But just to
Masoud, a minute is left.
Okay, thank you. So just to emphasize that these band powers are all above 0, so we have a significant correlation with these galaxy samples. So if we use galaxy catalogs without redshift cuts, then we don't get a statistically significant detection. So in the next few slides, I will describe the steps for obtaining p-value. The first step is to fit the measured cross-power spectrum, these band powers, to a template, and we use a template which is an exponentially decaying template multiplied by a constant, and this was motivated by the CHIME FRB beam transfer function. In this running example, I'm cross-correlating DESI LRG galaxies with our FRB catalog, and the level of cross-correlation is significant. Now the question is, how do we go from the template to a cross-correlation SNR? And to do that, we go from the template to an optimal estimator for this template in alpha, which I don't go into details in this talk, and we call it alpha hat. And then we measure something which is a local significance of the cross correlation in sigmas, SNR as a function of L. And this big L is the characteristic scale of our template. So here local means for a fixed choice of L characteristic scale and the redshift endpoint, Zmax in our case, without incorporating look-elsewhere effects in scale and redshift. In this example that I'm showing you, we see a significant correlation, SNR above 4 for scales that are about like 10 arc minutes, which is significant. But the question is, what is the global detection significance if we incorporate for look-elsewhere effects in angular scale and redshift endpoint? And to do that, we assign a global significance by maxing over the SNR local across 2 dimensions. Here we have angular scale L and also the redshift endpoint Zmax in the case of LRG. For the other 2 galaxy surveys, WISE and BGS, we vary zoom in. And after going through steps 1 to 3, we compute a p-value by asking the question of what is the fraction of max with SNR max greater than or equal to the SNR max of our data. And we get significant p-values, order of 10 to the minus 4. And that in the paper, we show that the level of cross correlation is consistent with an order 1 fraction of CHIME FRBs in the same dark matter halos as galaxies in those surveys. And here I'd like to emphasize that we are only detecting the 1 halo term. This slide, just to say a few words on the DM dependence of our results. If you just constrain your cross correlation analysis to the redshift range where you get the maximum signal, and then cross-correlate with FRBs binned in DM, then you get this plot in this slide. And this is significant result because there seems to be a statistical evidence for a correlation between relatively high DM FRBs, which constitute a modest fraction of our entire FRB sample, and low Z galaxies. In particular, our results are consistent with an order of fraction of our high DM FRBs being at redshift 0.4. And this is intriguing, as I said, given that most DM hosts, DM hosts from host associations have been shown to be between 50 to 200. And the question is whether this is consistent with direct host associations is the short answer is yes. And I won't take more time to go over details on this. Please let me know in the question period if you have more questions on this. And just to summarize, we predict that FRBs with extragalactic DMs greater than about 800 at redshift 0.4 will be found in direct association soon. However, future FRB surveys with higher sensitivity to fainter sources may show that FRBs with extragalactic DM greater than 800 will mostly come from redshift 0.8. So this DM dependence, we show that in the paper, the mechanism that can explain this DM dependence, and we show that propagation effects, which are associated with dispersion and scattering, are unlikely to explain the observed correlation. But a strong plasma and gravitational lensing can explain this, which in the paper we don't show actually the lensing calculations, but we postpone it to future work. And these are just possibilities that we would like to explore in future work. Thank you very much.
Thanks a lot for a great talk. We have time for some questions, and I can see some of them popping up in the Q&A. So Nicholas is asking, how does this analysis discriminate between DM host and DM cosmic? So DM cosmic is a combination of DM from IGM and Halo. And then he asked, could you clarify this in the context of mention evidence for excess DM host? Thanks and great talk.
Thanks for the question. So how does this analysis discriminate between DM host and DM cosmic? So in this analysis, what I'm plotting here is the extragalactic DM. So I'm basically assuming that the DM that I'm plotting here, I'm assuming that it's the addition of the two terms. And I'm actually trying to find the question. Okay, I found it here. So maybe I'm not sure what DM halo means here. DM halo, if Nicholas could elaborate on what DM halo means. Does he mean?
I think he meant from foreground halos along the line of sight of FRBs.
Mm-hmm, I see. Okay, so these are this effect has, we address this effect in the propagation effect calculations. So we show that propagation effects, basically electron anisotropies, you can think about in the foreground, cannot really explain this correlation that we see. But we show that the host halo DM of an FRB can contribute significantly if the FRB happens to be located near the center of massive halos. So foreground halos along the line of sight, in the paper we show that they cannot really explain the level of correlation that we see in this plot.
Okay, thanks for that. We have another question from Paz, who's saying very nice talk. And then they ask, does the correlation between FRBs and galaxies improve when you take away the lowest DM FRBs, which are presumably from lower redshifts?
That's a great point. Yes, it could. And this is actually what we did, like because as you remember, like these galaxy surveys in the low redshift end, Y supercosmos covers the redshift of 0 to 0.5, and BGS is at low redshift and LRG is at higher redshift end. And so what we do here is that we basically vary the redshift endpoints for the low Z galaxies. Galaxy surveys we vary Z min, and for LRG sample we vary Z max. And by varying these parameters, we are able to constrain the correlation and find the most significant correlation, the region that gives the most significant correlation. And so binning in Redshift certainly helps to boost the signal for sure.
Thanks for that. I can see another question from Ryan Shannon. Could the high DM FRBs be high Z FRBs lensed by foreground galaxies / clusters?
Yeah, that's a great point. So again, that's a possibility that that, for example, the actual FRBs that we are looking at with high extragalactic DM in this plot might have been lensed by foreground galaxies. So that's a possibility that we have yet to explore. We plan to do that in future work.
Thanks for that. Any further questions? Okay, if not, let's thank all the speakers in this session for their great, interesting talks. And I'll be posting all the questions on the Slack channel so we can keep the discussion going on there. And yeah, thanks and have a nice day, evening. And so the next session is the FRB coffee and tea break in Gathertown. So please join us there. And yeah, thank you very much.